couple things before going back to skating and physics. Monday, of course, is Martin Luther King Day, so there's no class on Monday. I will hold my office hours that afternoon if you want to come see me in Alderman Cafe, but otherwise, nothing's going on. That's one thing. The other thing is that I still haven't put up the first of the problem sets. I mean, homework assignments, problem sets. Somehow in physics, they're always called problem sets, so that's what I call them. They'll appear in the next 2 days or 3 days on the Wiley Plus site. And in answer to a question I had is you can go into the problem sets as often as you like, and you can pick off questions one at a time if you like and come back. They're not meant to be quizzes. They're meant to be thinking exercises to look at the questions, think about them maybe at your leisure, and then come back and ultimately answer them down the road before the deadline. All right? Any questions about class logistical stuff? Okay. Where we are, where I think we are, is looking at, in the context of skating, at the motion of a skater. A lot of the motion is this simple inertial motion. That is, the skater moving under the influence of no net force, zero net force, in which case the skater coasts, or equivalently, follows inertia, is inertial. They're all the same idea. So a coasting skater, because the skater is experiencing no forces, follows a straight line path at a steady speed, which we can now conveniently call a constant velocity. And yes, the velocity can be zero. So a skater at rest is also inertial. It's just a special case. Okay? So before I go significantly further with this, a demonstration I've had out here a couple of times and we haven't used is a hovercraft. So can I have 2 volunteers to be hovercraft pilot and pusher? Okay, please. So the idea is this, that you normally, when someone's sitting in a chair and you push them, they seem to move when you push them, and they seem to stop when you stop pushing them. This assumes you're not like mean. You are?
James.
James and?
Eddie.
Eddie. James and Eddie. So James gets to be pilot first. Have a seat. You're going to have to balance yourself sort of in the middle of the hovercraft, okay. And the on switch is just to run that. Okay. And Eddie's job initially is to be the net force. So we turn it on and go ahead. You should lift up on air, okay? And Eddie, now push James, and but you got to go stop him too, because your force causes accelerations, changes in velocity. It doesn't cause velocity itself. So when Eddie is not pushing James, James is coasting. So now you can trade places, yeah. Okay? So now it's Eddie's ride and James is the control. So once James gets Eddie moving, Eddie continues to move essentially for free, no push. And James's influences are just changing Eddie's motion. So yeah, you got to balance so that you're on the air. Yeah, you got to be here to undo the push too. All right. Yeah. There you go. Oh! Are you okay? Yay! Well, we're good. We're good. All right. Thank you, guys. Yeah, I get a sports-related injury here. So the notion is that when one or the other of them is riding, the motion continues. So you don't have to push on somebody to keep them moving. You have to push on them to start them, stop them, or change their direction. In short, to change their velocity. And so the pushes cause changes in velocity, which I introduced toward the end of last time. They're known as accelerations. All right? So in the absence, just to make a clean story of it, in the absence of a net force, so experiencing zero net force, you move at constant velocity. If you do experience a force, a net force, your velocity changes, and the name for that change in velocity is acceleration. Okay so far? A few things to think about with the constant velocity motion is, and then they do, we said last time, they go hand in hand. Net force 0, constant velocity. Constant velocity, net force 0. So with that in mind, let me ask you one of these questions, and it's here. In which case is an object experiencing 0 net force? Any questions about the question? I'll give you until, say, 40 seconds to get this. It's not everyone has the right answer here. 5, 4, 3, 2, 1, 0. Ho ho. Well, there's some E's in there. I'm not looking good for that. But there's a 50-50 split between all of the above and just the hockey puck. Look at the other three, the C and D. An elevator rider moving straight up toward the 10th floor at a constant speed. Is there velocity constant in that case? Actually, first I should say, to have net force 0, the only thing you have to look for is constant velocity. Are we okay with that idea? If an elevator rider going straight up to at constant speed, is their velocity constant or not? Think about that for a second. I mean, I guess I can ask you to come back to that then. I'll ask you to do this question again, actually. So just make sure you've thought about that elevator rider. And how about an escalator rider? So this is, instead of going straight up, they're going at some angle on the escalator, and again at constant speed. Try this one again, and talk to your friends about this one. So we got this split between the A choice and the B choice. See whether you all can figure this one out. I'll give you the whole minute to get it, to decide on this one. Five, 4, 3, 2, 1, 0. So there's been a significant shift toward A. And I'll tell you at this point, A is the right answer. And but seeing that there are a fair number of you worried about that C and D aren't in fact 0 net force, let's look at those because they're instructive. The hockey puck moving across the ice at constant velocity, that's B. That one is pretty much in your face, the same as a skater. So a skater coasting along the ice is comfortably a constant velocity motion, and associated with constant velocity motion is no overall force. And I can come back to talk about net force in a minute just to make sure everybody's comfortable with that too. But so the skater without any force on him or her, off they go. Hockey puck, same thing. It's just a inanimate skater. The elevator rider. The elevator rider is going up now. So the direction of travel of the elevator rider is different for us. And you might worry about gravity or something like that. But if the observation is that the elevator rider is moving at constant velocity, straight up, and at a steady speed, that is constant velocity. It's just an upward one. And the rule says, Newton's first law says that basically the constant velocity that associated with that is zero net force. So the elevator rider indeed is experiencing zero net force. And I'll come back to why that's, to tease that apart and to see why it's interesting. The same is true of the escalator rider. The escalator rider is heading up at some cockeyed angle, or maybe, yeah, it's up. I'm gonna have it straight toward the ground floor. Maybe it's down. It doesn't matter. They're moving at a constant direction, okay? It's a straight escalator. And they're moving at constant speed. Same direction, same speed. That's constant velocity. Zero net force. So I promise to say why those are interesting. If you think of the elevator rider, if they are moving up at constant velocity, all the forces on the elevator rider are conspiring to sum to zero. That's what net force zero means. It doesn't mean that you have no forces on you. It doesn't guarantee that. You can be net force zero if you truly have no forces acting on you. But the more common situation is you have several forces acting on you and they cancel. And that's what's going on in the elevator rider, and actually in the escalator rider. They're experiencing several forces and they cancel. It's pretty straightforward for the, for the elevator rider. I shouldn't say they're straightforward. The elevator rider is going straight up. And we'll see very soon, it's on my short-term agenda here, to talk about weight. The elevator rider is experiencing two forces, and maybe some others that we'll set aside as nuisances. The two forces that really matter are, they have a downward force due to gravity, and this one you've known about your whole life. It's called the person's weight, and we'll pin that down soon. But so there's a downward yank because of gravity in the Earth. If that were the only force acting on the elevator rider, they would fall. Bad news, okay? It's not the only force acting on it. The second force is from the elevator's floor, assuming they're not gripping things. The elevator floor is pushing them up just enough to cancel their weight. So the net force on them is exactly zero. And that's why they're coasting. They're coasting under the influence of multiple forces that sum to zero. And so they keep going at constant velocity. Is that okay? Same is true on the escalator. So the elevator, I hope you're all comfortable with the idea that they're being pulled down by gravity and pushed up by the elevator's floor. If we got rid of the elevator car, all of a sudden they would be in trouble. They would start to fall. They would no longer be net force zero. The escalator is a little wackier because they're heading, they were heading down, I think. They're going to the ground floor. They're heading down the escalator. They're moving steadily towards the ground floor exit. And their velocity is zero, velocity is constant, so they're net force zero again. Whatever forces are acting on them must exactly sum to zero. Well, they still have weight. Remember weight? They're being pulled straight down by the Earth's gravity. And that's the only other, there's only one other force. The force from the step of the escalator. Which way do you think the escalator step is pushing the escalator rider? I can do this, can't I? There's some way of having you, no, that's not it. There's a way of asking a question on the fly. I don't know how to do it. Let me get rid of this. I can't get that picture out of it. Show me with your hands which way the escalator is pushing the rider. It's either, in some direction like this. I want the direction. You're going straight up. It's straight up. So this is a fair, somewhat counterintuitive result is an escalator. When you're riding an escalator and you're in the middle of the escalator, we're not doing the start and stop yet. You're in the middle and you're just coasting down. And you're heading down like that. The escalator is simply supporting your weight. You're heading towards the exit, not because the escalator is pushing you that way. but because the escalator is allowing you to coast. You are aimed towards the escalator's exit early in your ride, and you're now just coasting there. Net force on you is 0. It's a little weird when it's going down. If it's going up, you may well have a feeling like you have to be pushed towards the exit. There's an up push towards the exit. No, the escalator's pushing you straight up, supporting your weight so that you can coast. And then you just continue to move as you were moving. And this is true not only in an escalator, it's true, say you're riding a cable car up into the mountains. As long as you're moving at constant velocity, the net force on you is 0, it's just supporting your weight. If you were riding a bicycle up a hill towards the top of the mountain, going at constant velocity, which is common situation, you're just pedaling along. There are lots of forces acting on the bicycle. It's a complicated story, but when you look at all the forces other than weight, they're pushing straight up because your weight is straight down. All right? Any questions about that idea? Hopefully it's intriguing to think through it, and hopefully it makes sense and it's intriguing to think about. Okay, so a couple more inertia things that are just useful to talk about before I move much further. Places in which you see inertia in action. One of them is let me get this out of here, is a hammer. We'll talk more about hammers down the road, but if you think about why does a hammer pound a nail into wood, you might think, well, it's gravity. No, it's not gravity, because you can pound a nail into wood the other way. So gravity, maybe it helps a little, maybe it hurts a little, but it's sort of irrelevant. It's really mostly an inertia story. You might also think that it's that you're somehow pushing the hammer into the nail, but you can get yourself out of the story. You can just, or bigger, okay? And actually I can come out the other end, I gotta be a little careful. And then, okay, you might think now again it's gravity, but if I were Thor, I can't pronounce the thing anyway. I can put this on the ceiling and throw it up and we could pound nails. So it has nothing to do with gravity, it has nothing to do with me really, except that I'm involved in somehow getting the thing going. It's really inertia. Once you get the head of the hammer moving, it wants to keep moving. Straight line, steady pace, constant velocity. That's true if it's in the absence of forces. In fact, eventually it's going to hit the nail, and the nail is going to push on the hammer, and the hammer's going to push on the nail, as we'll see. There are always pairs of forces that show up together, one on the hammer, one on the nail. But the hammer pushes like crazy on the nail, trying to keep going. The hammer's purpose in life is to keep going, and it just pushes the nail ahead of itself into the wood. Yeah? Isn't the hammer accelerating? There's lots of acceleration going on, that is true. So if you think about the story, I have introduced you to the concept of acceleration. The hammer's not moving, now it's moving, right? So I made it accelerate. So I'm exerting forces on it, causing it to pick up speed. Its velocity's changing. And at the moment it hits the nail, presumably I've got it moving as fast as it will ever move. And now I suddenly become a minor role in the story. I'm a bit part. And once the hammer has gotten, so it starts to touch the nail, the two of them start to push on each other. And my pushes become minuscule in comparison. They push like crazy on each other, and they do cause each other to accelerate. Forces, get ahead, to lay it out there. Forces cause accelerations. So, really more, to say it more complete, a net force causes acceleration. So if I'm the only thing influencing the hammer, I can cause it to accelerate. If the nail is the only thing pushing on the hammer, it can cause the hammer to accelerate. Often there are multiple things pushing on the hammer, in which case you have to add them up. You have to add the forces up. So add all the forces on the hammer. That will be the net force on the hammer, and that will tell you how it will accelerate, how its velocity will change with time. And during the impact, there is a lot of pushing, like serious pushing. and that causes serious acceleration of the hammer. So to do it in all its gory details and put numbers, then we'd be busy for a while. But the basic idea is pretty straightforward. I cause the hammer to accelerate from rest to traveling rather fast. At that point, I step out of the story, and the nail now pushes on the hammer and causes it to accelerate primarily in the direction opposite its velocity, and therefore it slows down the hammer. That push of the nail on the hammer slows the hammer down, but at the same time, the hammer pushes back on the nail. The forces come in a pair. And the force that the hammer exerts on the nail is overwhelming and causes the nail to accelerate in the direction of the hammer's push. Is that okay? Other questions about this? Again, questions are great. I mean, it keeps me in following stuff that's useful to you. So, one other important inertia trick, tool for a living that you should have in your repertoire. I think that's probably mixing metaphors, but okay. It's grease. It could be shampoo or something like that. The tube gets down to just a little bit left, and you're there trying to get that shampoo out. You squeeze it, whatever. What do you do to get the shampoo to drift to the opening so you can get that last little bit out? Well, many of you have discovered that you can start tapping it like that. And what you're doing is you're kind of coaxing inertia into doing something interesting, but you can do better. And so one that you may not know is if you really want to get the stuff inside to drift towards the mouth, get the whole system traveling fast in some direction. So give it a big velocity, say that way, and stop the tube. If you get everything moving and stop the tube, the shampoo won't know that the tube stopped. It'll just keep going. It's got inertia. So, just that kind of a motion. And actually, the best possible, which is a little bit sophisticated to think about, is to go around a circle. Now, why is a circle so good? It's because any change in velocity is an acceleration. And it's I hope it's easy to see that if I go from motionless to moving, speeding up is an acceleration. And it was caused by a net force. Similarly, slowing down was an acceleration caused by a net force, in this case, the wall pushing on me, all right? But the other one, not to be neglected, that is an acceleration, is a change in direction. So if I'm going this way and then I turn, this kind of motion, I'm accelerating the whole time. So movement in a circle, objects that are free of net force do not move in a circle. They can't do it. To change the direction of your travel, you have to have something push you. So if I'm doing this, you can know his velocity is not constant. Something weird is going on. Something is pushing him around in a circle and causing him to accelerate the whole time. This something happens to the floor and friction. If this were ice, if I were in a skating rink, I could not do that movement. I couldn't go in a circle without friction. This is, if it's supposed to snow on Saturday, something like that. Tomorrow, if you lose friction, which you do during snow and ice, traveling in directions that involve accelerations becomes problematic at best. You can't do it. So it's easy to travel at constant velocity because you get that for free with no force. So cars tootling down the road in a straight line at a steady pace, having already picked up speed, so the story starts with them moving, and off they go. This is easy. It's the stopping, it's the starting again. Whoa, he says as he steps on something that has bad friction, or traveling in circles, turning. So cars go off the road when they start, stop, or turn, and are unable to get the force they need to do the turn. All right? should it snow and you go out on the roads and look around, you will notice that cars tend to go off the road in the direction that inertia prefers, that inertia takes them, which is usually on the outside of turns. So if the turn is, say, away from you, like this, if you lose traction, no friction, you go inertial. The road turned that way. I'm on the outside of the road. Okay? They're not on the inside. So yeah, you can buy your house on the inside of the turn and not worry about cars driving through your bedroom. If you buy your house on the outside of the turn, you're going to have visitors. All right? So getting back to this trick, I'm taking the tube around the turn, and the shampoo doesn't know about, it isn't getting the message that we need to make the bend. It's trying to go straight according to inertia, and it ends up at the cap. It runs, it can't keep, if you leave the cap off, and maybe you have done this, a bottle of ketchup, whew, uh-oh, it's all over, it went straight. Inertia trouble. All right. Question about where to find the problem set assignment. When I put it up there on Wiley Plus, it will be on the book's website. I think it shows up on a calendar section saying it's due in the near future, and I think it shows up among the modules. So there's home, there's a tabbed list of things to do. There's home and there are modules, and in the modules, I think their problem sets are visible. Okay. Again, you can send me messages and I'll try to catch them. Send me messages electronically. All right. Well, I told you last time about, I introduced 4 of the physical quantities I wanted to get through. I needed 3 of them to get to Newton's first law, and they were position, velocity, which is the rate at which position is changing with time, and finally force. Force being the influence that causes velocity to change with time. I then introduced acceleration. So acceleration is the third in the sequence of position, which is where I am, velocity, which is how I am moving, how my position is changing with time. And the third step in this is acceleration, which is how my velocity is changing with time. And I started to illustrate that. Let me just make sure it's clear to you when I'm accelerating and how. I've talked some about it already, but let me just get it clean here. I'm going to show you again with my hand when I'm accelerating and in which direction. And I'm going to do it slowly because if I go fast, I'll just confuse myself. And my goal in doing this is to help you distinguish acceleration from velocity. They are different. They're related because acceleration is how velocity is changing with time. So let me accelerate to your left initially. Right now I would start with 0 velocity. So in order to develop any velocity other than 0, I have to accelerate, which will be caused by a net force. So the net force, again, is the floor. You can't see it. We'll just, it's there. So I'm going to start accelerating. So here you go. I accelerate. And if I keep doing it, I'll go faster and faster, but I'm going to stop. I've stopped accelerating, but that doesn't mean my velocity is constant. Uh-oh, coming to the wall. Now I have to accelerate this way. Now I can keep going. Okay? So acceleration shows you how and in which direction velocity is changing. Uh-oh, better accelerate. Back. Let me bring myself to slow so I can talk. Oops. So I coast. In between accelerations, I coast. And during accelerations, my velocity changes with time. And if I accelerate opposite my velocity, which I'm doing right now, I actually can come to a stop briefly and then even start picking up speed in the other direction. If I accelerate at right angles to my velocity, I start to turn. I don't make a hard, let me stop the story for a second. Acceleration doesn't immediately cause velocity. Forces don't cause velocity, they cause changes in velocity. So if I'm already heading to your left and I accelerate toward you, I don't suddenly go and turn. Instead, I cause a gradual evolution in my velocity. So let me do it really slowly so I can talk through it. So I'm going to start off to your left, And now I'm going to accelerate right toward you, exactly toward you. You'll notice I ended up, end of the story, I ended up heading at a cockeyed angle because the acceleration toward you didn't cause me to move toward you. It caused me to start to develop some movement toward you in addition to whatever I was doing already. So I headed off at this angle. All right? So that's acceleration. Hopefully you can see it. You can watch things around you accelerating and mentally distinguish it from velocity. Velocity is easy to see. Position is the easiest to see. Velocity is pretty easy to see. You just watch the thing move. Acceleration is subtle. You have to watch the movement change in character. Different speed, different direction, or both. All right? I should say about acceleration. It's caused by net force. So net force causes not movement, not directly, but change in movement. So net force causes acceleration, and the acceleration is exactly in the direction of the net force. So if you look at the forces acting on something, on me, for example, a bunch of people pushing on me or pulling on me, I don't respond to them individually, I respond to their sum. And the sum has to take into account the direction which they're pushing or pulling, which makes life a little complicated. It becomes a geometry problem, potentially with trigonometry in it, but the details aren't very important. Clearly, if two people pull me, one this way, like that, one like that, I am going to go somewhere, I'm going to accelerate somewhere in between. So that's fairly intuitive. Net force causes acceleration in the direction of net force. There's one other physical quantity to bring up that's important, and that is the same net force acting on different objects will cause different accelerations in those objects because those different objects have different amounts of inertia. And the measure of inertia, how much inertia an object has a name. It's called mass. So an object's mass is the measure of how much inertia it has. I also think of it as resistance to acceleration. So something like a baseball has a small mass, meaning it's pretty easy to make this guy accelerate. If I exert a force on it, its velocity changes with time, and it doesn't take a very big force to get a pretty significant change in its velocity. On the other hand, a bowling ball, well, this is a pretty light bowling ball. All right, this guy is harder to make accelerate because it's got more mass. And the way I mentally think about sort of measuring mass is to shake something. So why shaking? If I shake the baseball, I'm causing it to change from heading away from me to heading toward me, to heading away from me, toward me. That's big changes in velocity in short amounts of time. I'm causing a lot of acceleration. And in doing that, I'm discovering the relationship between the force I exert on it and the acceleration that results. And I'm just discovering, not a lot of resistance to that acceleration. That is, a little force causes a lot of action. On the other hand, the bowling ball's harder, right? It's harder to shake. So you can, at least conceptually, you can measure the mass of an object by shaking it. All right? Note about mass. It's completely an inertial idea. It has nothing to do with gravity. You can get rid of gravity entirely. You can go to deep space if you like, and this bowling ball will be harder to shake than the baseball. Incidentally, with astronauts in orbit or something, it's hard to weigh an astronaut. You can't have them stand on a scale and get any reading because they're moving. Their motion's complicated. The simple weighing trick doesn't work. So how do you determine how much astronaut there is there? You shake them. So astronauts have historically been they're not weighed. Their mass is measured, which ultimately is a very good measure of how much astronaut there is. A massive astronaut is hard to shake. And it does result, it is the result of eating a lot of food and not losing, you know. On the other hand, a low mass astronaut is easy to shake. And so they've made gadgets that have flown in space that had, their only purpose was to shake the astronaut and figure out how much astronaut there is there by measure of mass. Okay? We'll come to weight, you know, very soon. Weight really has to do with gravity. So we in common life use these two notions kind of interchangeably. You go get a lot of mass of flour, you go get a lot of weight of flour. Who cares which one you're using? It turns out there's a good reason for not caring very much, but they're different concepts. So mass is the resistance to acceleration. And that then gives us or leads us to a very simple relationship between the net force on an object and its mass and the acceleration that occurs because of the net force. This is given the name Newton's second law. Many of you have encountered it before, written out as an F equals ma type arrangement. But that arrangement it's not my favorite form. My favorite form of the arrangement, and to keep it as concept so it really maybe sticks, or hopefully sticks, is if you want to know how an object's going to accelerate, figure out the net force on the object, and divide that net force by the object's mass. That ratio is the acceleration of the object. So it's force over mass equals acceleration. The force is what is the cause. The mass is the resistance, the opposition to the cause, how much it hates to accelerate. And the result of that relationship, force over mass, is the acceleration of the object, how much its velocity changes with time. There's direction in that relationship. The force has a direction, and so does the acceleration, and they're the same direction. Okay? The F equals ma relationship is the same one I just said. Let me just, okay, I'll go really old school and use the, so I just said that the force, and it's net force over the mass of an object. So it's the net force on the object, not the net force on the moon. It's the net force on the object, one we're paying attention to. The mass, again, the mass of the object specifically. Net force on the object, the mass on the object, that equals the acceleration of the object. And so this is cause, opposition, result. So cause and effect. For some reason, physicists decided, division is ugly. Let's get rid of the division. So we'll bring the mass over to the other side of the equation and stick it over there. So we get F equals AM, or MA. I should just go full hog here, MA. And so now they've got cause and effect. They've gummed up the equation. It's not cause on one side, effect on the other. It's muddled. But it doesn't have division in it. Well, so anyway, I've said my harangue. You okay with it? All right. So, and that's a quantitative result. This class, although we don't do numbers very often, is nonetheless often quite quantitative. That means that's an exact relationship. If you tell me the force on an object, for example, the object's weight, which is the force of gravity on that object, and its mass, which actually we might want to know, the acceleration is precisely the force divided by the mass to all possible digits. I'm not making quite as clear as I'd like, but basically often you can name quantities rather than measure them and write them out as some long 10-digit number. And so the named quantities arranged properly give you exact quantitative results that are even more accurate than if you measured the numbers and wrote them down to the best of your ability to measure them. These are exact results, perfectly quantitative. All right? So for a skater to start or stop or turn, they need a net force on them, and their acceleration in the response to that net force will be exactly that net force divided by their mass, and off they'll go. All right? So I've got 5 physical quantities done, hopefully, and any questions on this? The movement of a skater, really, in this story. Okay, well, let me go on and talk about falling balls. And falling balls is, okay, in effect, you can turn a page and say it's a whole new story, but it's the same. These are stories now, but we're shifting into a new context. The same physics follows us. And the physics is this, that we know that this ball has a certain mass, so it's certain difficulty getting it to accelerate. And if you exert a force on it, it will accelerate. It will need a large force to get a decent acceleration out of it. But that's what will happen. Well, what force is it experiencing? Well, right now it's experiencing the forces that involve my hand, but let me get it out of my hand. Let me go over to smaller ball. I don't want to throw that guy around for pretty obvious reasons. Do I want to do this? Yeah, let me ask this question here, and then we'll pursue it further. The question is this guy. So if I throw a ball upward, so the story's asking about not yet, not this moment, but ready, get set, now. While the ball was heading upward, and we're getting rid of the air is a nuisance, we'll just not worry about the air. As the ball is heading upward, is there any force pushing the ball upward? You okay with the question? Question about question? Okay, see what you think. The other version of this arrangement that's fun is I can turn on the graph while you're still choosing. Yes, you can turn on E and, all right. So what do you think? Is the majority really right there, A folks? E folks? All right, I'll stop. Too much fun. The answer is no, there's no force pushing upward on the ball. Again, we're leaving air out of it, which is a nuisance. So why is the ball going upward? You tell me. I'm hearing a few inertias there. It's inertia, right? I get the ball moving, and during that time, I'm exerting forces on it. It's definitely not inertial. It's accelerating like crazy. So if we do this slow motion, I'm pushing like crazy on it. It's accelerating upward faster, faster, faster. Then it leaves my hand. I can't go slow. Then it leaves my hand. It's moving upward, continuing to move upward because it was moving upward. Object in motion tends to keep in motion, straight line, steady pace. It's trying to go upward. And if there weren't for something, not a nuisance anymore. If it weren't for gravity, once the ball left my hand, it would be net force 0. It would coast. It would go all the way to the ceiling at a steady pace, straight line. That's what inertia has in mind for it, right? That it doesn't do that is because of gravity. But I asked, is there an upward force on it? And the answer is no. So the ball doesn't need anything to push it upward, to keep it moving upward. It does that because that's what inertia, that's our universe works. Things have inertia. They have a tendency to keep doing what they're doing. So on its way up, that's inertia carrying it upward while the Earth's gravity is gradually pulling it, causing it to accelerate downward. Pulling it downward. Are you okay with that? Questions about that? Ask me if it's making sense. Is inertia not a force? No, inertia is not a force. We will see down the road that inertia is really related to what's known as momentum. So I'm giving the ball upward momentum, sort of to get ahead of ourselves, which is okay. I'm giving the ball upward momentum, and the Earth's gravity is slowly pulling down and taking away that upward momentum. But while it's moving upward, it's not carrying force with it. any more than it's carrying in, yeah, it's not carrying force. The forces occur between objects. Inertia is not about between objects. It's the characteristic of a single object. It's got inertia, which is related to it's got momentum. And so the ball carries momentum with it. It doesn't carry force with it. The force is, yeah, I'm making this more complicated than it needs to be. Inertia really is more of a, finally, is a concept that we can't pin down and measure. We will see, though, that momentum is something you can pin down and measure. It's just a more complete notion. Okay, so when I get this guy going, it continues to rise for free because of inertia, because of momentum. And it is being pulled down by something. That something is really the first named force for this class. And it's called the force due to gravity, particularly the Earth's gravity. But that's a long-worded thing, windy thing. So instead we call it the ball's weight. So just to set it once and for all, the ball's weight is exactly the same idea as the force of the Earth's gravity on the ball. Okay? So the ball is experiencing one and only one force while it is out of my hands. And again, neglecting the air. That is the downward force due to gravity. And the result is a downward acceleration. So oddly enough, the ball, which is traveling upward and has an upward velocity, initially at least, has a downward acceleration. Velocity upward, acceleration downward. That means the ball is slowing down. Sometimes just in common language, or even for physicists, we call this sort of acceleration, the acceleration opposite the object's velocity, we call it deceleration. That's nothing. Deceleration is not a new concept. It's just a special case of acceleration. It's acceleration opposite the velocity, and it always causes the object to slow down. So I can do it here on the horizontal floor. Let me show you deceleration. I've already showed it to you. Let me get started. This is not deceleration. This is picking up speed. Now I'm going to decelerate. I'm accelerating to your right while moving to your left. That brings me to a stop. I decelerated. Just a special case of acceleration. All right? So the ball, when I'm throwing it upward, is accelerating downward, and it did come to a stop momentarily up there at the top. At that moment, it finally ran out of upward momentum, and for an instant, it was motionless. So to sort of wrap this up for now, when an object's experiencing only one force, its weight, it's a falling object. That's what falling means. I mean, in my vocabulary, falling means experiencing only your weight and therefore accelerating in response to it. And one of the amazing things about, so the whole time this ball is above my hand, it's accelerating downward, it's falling. So it's falling while it's going upward, it's falling at the top when it's momentarily motionless, and it's falling as it descends. It's all falling, and actually if the ball goes like this, it's still falling. They're just complicated variations on the concept. They're still falling. And one of the crazy, wonderful things about falling is that if I drop this little ball, it experiences its little weight, so the net force down is little, but its mass is little. So the influence that's causing acceleration is little, and the resistance to acceleration is little, so it accelerates downward at a certain rate. If I drop this bigger ball, whoa, it's got a much bigger downward force because it weighs more, it's got more weight. So that by itself would make the bowling ball accelerate like crazy. But it also has more mass. It's hard to shake. So that makes it accelerate terribly slowly. So bigger force, which tends to boost acceleration, bigger mass, which decreases acceleration, they cancel. This guy accelerates downward at the same rate as the ball. I'm tempted to drop them. I can't do it. They get downstairs comes upstairs and says, are you okay? But if I can do the other version. If I drop these guys, they go together, even though they have different weights and different masses. It turns out that no matter what, I've got a pocket full of change out of reach, but if you drop the quarters, nickels, dimes, the gold doubloons, they all go together because the ones that are bigger, they have more weight, so they go faster. They have more mass, so they go slow. They cancel. All right? So we'll do that right on, not on Monday. We'll do it on Wednesday.